Hey, in this video, I would like to show you how to solve all problems in the practice exam. Some problems I will not solve in detail, but I will guide you how to solve that. Okay, so watching this video, practice a little bit, and I think you will be fine for the final. The first question is about homogeneous system of linear equation. 2x1 plus 4x2 minus 13x3 equal to 0, and x1 minus 3x2 plus 16x3 equal to 0. So, we solve this system from time to time, right? Even we do that in the last chapter when we need to find all eigenvectors for some eigenvalues. So we need to solve homogeneous system of linear equation. Homogeneous systems always have solution that is 0, 0, 0. In case if the rank of the coefficient matrix is less than the number of variables, the homogeneous system has infinitely many solutions. So in this case, it's obvious that system has infinitely many solutions because the rank should be less than or equal to 2, right? But at the same time, we have 3 variables. So let's make reduced rows or just row echelon form from this. I would say I can interchange the first and second equation around 1, 93, 16, and then 2, 4, 90, 13, right? I multiply the first row by 92 and add to the second. I will get the following 193, 16, and then 0 in here. 92 to this, I get 6, 6 plus 4 is 10. 92, I have 32, add to this. So 32 add 13, I would have 45, right? Negative 45. So this is a row echelon form. From here, I can take the second equation. I solve that, and then I plug it back to the first one. So we call back substitution. Do you remember that? We call back substitution, and we solve x1. I have 10x2 minus 45x3 equal to 0. From here, I can solve x2 is equal to 4.5x3, right? 4.5x3. I plug it back to x1. I have x1 equal to 3x2 minus 16x3. And so that is 4 times 4.5x3 minus 16x3, which is this 3, 1. So I have 13.5x3 minus 16x3, and 13 minus this, I get 2.5x3 negative, right? And then the general solution looks like 92.5x3, x2 is 4.5x3, and x3, or you can write x3, -2.5, 4.5, and 1. So that is the solution space. The solution space has dimension equal to 1. Alright? The second question. Solve the system using Gaussian elimination with back substitution or Gauss-Jordan elimination. If the system has an infinite number of solutions, express x1, x2, x3 in terms of parameters. So let me write the matrix form of this system right away, right? That is 2, 0, 3, and here 3. And you have 4, -3, 7, and 2, and then 8, -9, 15, and 17. So if you remember the reflection journal, the first reflection journal, you will ask about the condition between the rank of coefficient matrix and the rank of the augmented matrix. And that condition would imply, how many solutions the system has, right? Because if the rank of the coefficient matrix is equal to the rank of the augmented matrix, the system has solution. And if that ranks are equal to the number of variables, so the system has unit solution. If the rank is less than the number of variables, the system has infinitely many solutions, right? If the rank of coefficient matrix is not equal to the rank of augmented matrix, the system does not have any solution. So let's make row echelon form of this matrix, and then we'll see the rank of coefficient and augmented matrix are equal now. So here, this is 2, I multiply by -2, add to the second, right? I get the following. 0, 2, 0, 3, and here 3. I have 0 in here. Here is still -3. -2 add to this, I have 1. -2 add to this, I have -4. And I multiply the first row by -4, add to the third. I get 0 in here. Here's -9, 4. Add to the third, I have 3. And then -4, 12. This is interesting. -4, so I have -12. Add to this, I have 5. Okay, and then we multiply the second row by -3, add to the last. So I have 2, 0, 3, 3, 0, -3, 1, -4, and then 0, 0 in here, and then 0 in here. But this give us 12 plus 15 should be 17. So in case on the final exam, you can use calculator to find reduced row echelon form or row echelon form of this matrix. And based on this form, you will say the rank of coefficient matrix is equal to 2, because in the coefficient matrix, you have only 2 non-zero rows. But the rank of augmented matrix is 3. So less than rank of augmented matrix. So that means the original system does not have any solution. No solution. Right? Next problem. We have matrix A, which is 1, 1, -2, 1, 0, -1, 4, -1, and -1. And then B is 5, 1, and 0. They ask us to express the column matrix B as a linear combination of columns of A. So as a linear combination, meaning this vector is linear combination of this column, this column, this column. That means we have to solve, suppose that is linear combination. So we can find coefficients if we can solve the following system: 1, 1, 92, 1, 0, 91, 4, 91, 91, and here we have 5, 1, and 0. So don't forget about that. Because if we want to express some vector as a linear combination of others, we have to write those vectors in the column form. Okay, in the column form. So, and we need to solve that system. One system has solution. That vector is a linear combination of this column, and this column. If this system does not have solution, that means B is not a linear combination. Alright? These techniques, are used also when we need to check linearly independence, or if a vector can be represented as a linear combination of all the vectors. So you solve that yourself, okay? Just the idea how to do that. The next question, that is -1, -1, 2, 1. Here is A, here is, alright, 1, 0, 0, 1. So we have this question on the first test. And actually, when we cover the second module, we study how to go from one basics to another, and we need to find transition matrix. So I hope you still remember that, how to find transition matrix, right? In order to find A, in this case, basically this is how we go from one basics to another. From one basics to another. I remember on the test, some students write in general formula 91, 91, 2, 1, and then here I1, 2, I1, I1, 1, I1, 2, I1, 2, 1, I2, 2, and here I have 0, 1, 0, 1. And then they multiply them all together, they get 4 equations. Of course, you can solve that way, but don't do that because we have a shorter ways to do that. So the shorter ways to do that is, but let me explain a little bit about this and about transition matrix. So if you apply this matrix to the first column, you get the first column here, right? That means you express the first column as a linear combination of this column and this column. Make sense? If you apply this to the second column, means you express 0, 1 as a linear combination of this column and this column, and A1, 2, A2, 2 are coordinates of 0, 1 in this basics. See that this vector and this vector are linearly independent. So basically we say, finding A is transition matrix from the standard basics, that means from this basics to another one. Right? So in order to do that, you just need to write -1, 2, and 1 in first, and then 1, 0, 0, 1 the second, and you use row elementary operations to get the identity matrix in this side, and then at that time here you would get A. Make sense? So this is how we can find transition matrix from one basics to another. Okay? If this is a new basics, you write those vectors in the column form. In the column form, that is new basics, right? And this is the old basics. Whatever you have, in this case you have 0, 1, and 1, 0. So you write the new basics in here, the old basics in here, and then you use row elementary operations to get the form identity. I mean this identity, and here is the transition matrix. Alright, you can use calculator, no problem with that. Okay, move to the next question. Find the inverse of the following matrix if it exists. This is pretty easy. 1, 2, 3, 5, right? So they ask us to find the inverse of this matrix if it exists. How to check if a square matrix is invertible or has inverse? The easiest way is to check determinant. So in this case, determinant of A is 5 minus 2 times 3, which is -1. The determinant is not 0, means A is invertible, right? Of course, you can find inverse matrix, based on the same technique in here. Let me remind you about that. You can write 1, 2, 3, 5, and then 0, 0, 1, and you use row elementary operations to get the identity in here, and here is the inverse, right? But again, for 2 by 2 matrix, you have very, very good formula. You can use cofactor. You can use cofactors to find the inverse. So cofactor to find the inverse, the formula, I hope you still remember that, and that is 1 over determinant times adjoint matrix of A. So what is the adjoint matrix of A? There is one determinant. I have cofactor Aij and then take transpose. Right? Cofactor Cij, take transpose. So what is for example, for the first entry, the determinant is -1, right? So I write -1 over 1. Let's say, what is the cofactor of 1? Cofactor of 1 means you erase this column, you erase this row, and you get 5, right? You get 5. But this is not only 5, because the position here is 1, 1, so you still have -1, 1 plus 1 in here, which is 1. So that's why we just have 5. The second one, the cofactor of 2. 2 is in the position 1, 2. So here I have -1 and 1 plus 2, right, which is -1. And then I erase this row, erase this column, I have 3. With -1, I have -3 in here. Similarly, for 3, I have -2. And for 5, I have 1. But don't forget, take the transpose. So that means I have -5, 2, 3, and 1. That is the inverse of A. All right. Move to the next. Find the value of K such that A is singular. So here A looks like 0, K, 1, K, 5, K, 1, K, 0. What does it mean A is singular? A is singular means A is invertible. A is invertible or A is not invertible? Right? So singularity, let's say if A is singular means A is not invertible. It's not invertible. If A is not invertible means the determinant of A is 0. Okay, don't forget about that. So singularity and determinant is very connected. So basically, you have to find K so that determinant A is 0. Alright? And here, I think this 3 by 3 matrix, we have different methods to find determinant. Let me remind you how to use diagonal, right? Diagonal method to do that. So you find entries in here 0, 5, and 0, then K and 1, then K and 1, right? All 3 terms with positive sign. That is with respect to the main diagonal. With respect to another diagonal, you find all products, but you add negative sign here. For example, here 1, 5, 1, so you have -5. K, 0, you get 0. K, 0, you get 0. So once you find determinant of that, you set it equal to 0 and to find all K's. Okay? So that's what we need to do. Next, find the adjoint of the matrix. Then use that adjoint to find the inverse of A. This is what I just showed you in the previous problem 5. So probably on the final exam, I will not give you 2 problems like that. All right, next question. We'll talk about spanning set. So you have some set in R3, which is 1, 9, 0, 0, 0, and 1, and then 91, 9, 0. Determine whether set S spans R3. If the set does not span R3, then give a geometric description of the subspace that it does spans. So about geometric description, we had that conversation before, right? But on the test, I remember I gave you that if that set does not span the whole space, so you need to find at least one linearly independent subset of S, or I would say find a basics of a subspace, right, generated by vectors in S. Make sense? So in order to check whether S spans or not span R3, in this case we have three vectors, right, in R3. So the easiest way to do that is to find determinant, because the matrix from these three vectors is 3 by 3. This is perfect. So I can write 1, negative 9, 0, 0, 0, and 1, negative 1, 9, 0, right? I check determinant of this. If the determinant of this matrix is 0, means this vector and this vector and this vector are not linearly independent. They are linearly dependent. So they cannot generate, they cannot span the whole R3. Make sense? If determinant is not 0, all three vectors are linearly independent. They span the whole R3. Alright? So let's check that. Determinant of this, I can span, I can use this column. So this position is 2, 3 with negative. Determinant of this, erase this. I have 1, negative 9, negative 1, and 9. The determinant is 0. So that means these vectors are not linearly independent. Okay, so the second part of the question is give some geometric description about a space, right, generated by this. So that means we have to find minimum linearly independent subset of S. In order to do that, I need this matrix and I need the row echelon form of this. I need the row echelon form of this. Don't forget, don't be confused in this case, because I wrote these vectors in the rows form, right? In the row form. I don't write them in the column form. Don't forget about that. I wrote them in the row form because when I use row elementary operations and I use row forms, the row space does not change. So that's why in the row echelon form we can use two non-zero rows or all non-zero rows to form a basis of the row space. Alright? So let's make row echelon form of this. So here I have 1 here, negative 1. I just add this to this. I get 0 in here, 0 in here, 0 in here, right? So finally, this is the row echelon form. Perfect. This vector and this vector are still in the subspace generated by vectors in S. So I would say S, the span, the linear spans of S, right, is a subspace. And that subspace has this vector and this vector as bases. That's it. That's how we can describe. And the dimension of that subspace is equal to 2. Alright. Let's move to the next question. We have P2. And then in P2 we have S. 1 minus x, 1 minus x squared, and then negative 1 minus 3x plus 4x squared. So P2 again, that is the vector space of all polynomials of degree less than or equal to 2. So here we have 3 polynomials, right? And we know P2 is isomorphic with R3. But again, we have to be careful when we translate from P2 to R3. Because it depends on the order we use, right? Because, for example, this polynomial, negative 1, negative 3x plus 4x squared. If you pull out coefficients from here, right, in this order, you would get negative 1, negative 3, and 4. Right? And then you keep the same order. From here, you get 1, and here 0 and negative 1. Because we don't have any term of x, right? So that is, the coefficient is, of that is 0. Then from here I get 1, negative 1, and 0. So basically, we need to check if these 3 vectors form a basis of R3 or not. If these 3 vectors form a basis, means these 3 polynomials form a basis for P2, right? We have 3 vectors in R3. Set matrix and then take determinant. If the determinant is 0, they will not form basis because they are not linearly independent. If the determinant is not 0, they are linearly independent and they form a basis. Right? So you do that yourself. You take this guy 1, negative 1, 0, 1, 0, 91, and 91, 93, and 4, and 5, determinant. Done. Next question. So I've solved this question and we stop this video and maybe we have to record a new one. We have vector v and u, and where u is 1, negative 9, and 1, we have to determine all vectors v that are orthogonal to v. From this question, we can imagine that we are moving to inner product space, right? Because before that, we work with vector spaces. We don't have any measure, we don't have any distance. And now we have measure, we have distance, and we have inner product. And thanks to inner product, we can define orthogonality. Two vectors are called orthogonal if their inner product is equal to 0. Alright? So in this case, we consider vectors in R3. So that means we just use dot product. Just use dot product. If I said V is V1, V2, V3, right? I say since V is orthogonal to U, means dot product of V and U is 0. So I have V and U is 0. From here I get 1 V1 minus 9 V2 plus V3 equal to 0. So that means the set of all vector V's that are orthogonal to U should satisfy this equation. That is nothing but the solution set, the solution space of this homogeneous system. Make sense? So you solve that, you write, for example, you write V1 equal to 9 V2 minus V3, and the general solution of this is 9 V2 minus V3, V2 and V3. So from here, you can put out two vectors in the basics. For example, here you have V2. For V2 here you have coefficient 9. In this case you have 1, but in this you don't have anything, right? V2 plus V3. In here we have negative 1 V3. Here you don't have V3. Here you have 1 V3. So basically, all vectors V that are orthogonal to U are in the subspace of R2, which is generated by this vector and this vector. Done. The next question. Apply the Gram-Schmidt autonormalization process to transform the given basics in Rn into an orthonormal basics. Use the Euclidean inner product and use the vectors in the order in which they are given. So in this problem, we are talking about Gram-Schmidt process. I already explained about that in the previous video, you know. So in this case, in this problem, I just give you a very brief solution of this problem. So let's say in B we have 0, 0, 6, and then 0, 1, and 1, and then 1, and 1, and 1, right? We call this is V1, this is V2, this is V3. So we put U1 equal to V1. We fix the first vector. And then we have U2 is V2 minus projection of V2 on U1. So basically we just subtract the orthogonal part of V2 on U1. Then these two vectors are orthogonal. What is the projection? where projection of V2 on U1 is U1 is dot product V2 U1, right, divided by U1 square. I mean, this is norm, right? Or sometimes you have U1, or sometimes you just write V2 U1 and then U1 U1 and then times U1. That's it. And U3 equal to V3 minus projection of V3 on U1 and projection of V3 on U2. So we apply the same idea. We take V3, we subtract x orthogonal parts on U1 on the previous orthogonal vectors, U1 and U2. Here we should not use V1 and V2, don't forget about that. If you use V1 and V2, you will not have vector U3 orthogonal to U1 and U2. So we will not have orthogonal basics. And after this process, you have to normalize. You have to make unit vectors from U1, U2. So basically you have take U1 divided by norm of U1. You have U2 times norm of U2, and you have U3 times norm of U3. So all these three vectors are unit vectors. They are orthogonal and unit vectors. They form an orthonormal basics from these vectors. Okay. So move to the next. In the next question, they ask us to find coordinate matrix or coordinate of some vector related to the given basics. So here they have -5 and 6, right? And then 3, -2. And vector is -17 and then 22. They ask us to find x in B prime. So what does it mean? Okay, let's say this coordinates, right? X equal to -17 and 22. That is the coordinate of x with respect to the standard basics, which is 1, 0 and 0, 1. And now we go from the standard basics to the new basics, and we need to find the coordinate of this vector in the new basics. So basically, we need to find the transition matrix. We need to find the transition matrix, right? So how to find transition matrix? We know that. We just solved that previously. We write -5, 6, 3, -2 in here, and then here we have 1, 0, and then we have 0, 1, right? We write this form, we use row elementary operation to transform this guy into identity. And then, in this side, you have transition matrix. Alright? Once you find transition matrix, you apply the transition matrix to the old coordinate. You get the new coordinate in the new basics. Times. Right? So you do that yourself. I will not do that. This 2 by 2 matrix. You can use calculator or you can use, just operations. Okay, next question. In the next question, they give us some linear transformation T, x and y, which is -x, y plus y, and then -x minus y. And they ask us whether the linear transformation is invertible. If it is invertible, find its inverse. Okay, let's remind about that. So we know that for each linear transformation, there is one and only one matrix, right? We call representation of that linear transformation. And from here, we have matrix A. I call AT is equal to -1, 1, -1, and -1. So I take coefficient 1, -1, 1, 1, and here -1, -1, -1. If this matrix is invertible, the linear transformation is called invertible. If this matrix is not invertible, our linear transformation is not invertible, right? And in case if this guy is invertible, we can find A inverse, right, of T. And this matrix is, is the matrix of the inverse of this linear transformation. Make sense? Let's do that at least one time, and we'll see. So this matrix is invertible or not? Interesting. In order to do that, we just need to check determinant, right? The determinant of AT is what? 1, 1. So -1 is 1, 1 plus 1 is 2, which is not 0. Means AT is invertible. So that means AX AT to -1. How to find that? AT to -1 is equal to 1 over determinant of AT, and then cofactor transpose. So determinant is 2. That means 1 over 2. Cofactor of this guy is -1. Of this guy is -1 with negative. So I have 1, right? I have 1, but I take the transpose. So I get this -1 and 1 in here, and then determinant of this guy is -1, of this guy is 1, right? So 1 with negative, so I take the inverse in here. Don't forget that we need to take the transpose. So from here I can write the T inverse x and y equal to -1 over 2x minus 1 over 2y, and then 1 over 2x minus 1 over 2y. You see, I just multiply 1 over 2 into these entries, right? And I just go back. For example, here, -1, 1. I have -1/2, -1/2 x, -1/2, -1/2 y, then -1/2 x, and then 1/2 y. Done. Alright, so I think that is enough for this video, and that's what we did. And that's what you need to review for the additional test. Alright, and what happened from question 14? That's what we cover right now. So you can see practice test. You can see video, watch video for practice test. In question 14, they give you 2 by 2 matrix and find all characteristic, equation and eigenvalues, and then eigenvectors. So we know how to do that. In the next question, they give you some linear transformation from P2 to P2. We just had that problem from P2 to P2, right? Where's that? Or maybe in the practice test. And so you pull out the matrix of this linear transformation, and then find all eigenvalues, eigenvectors of that matrix. Yeah, watch the video for practice test. Next question, for the matrix A, find if possible non-singular matrix. The same, right? There's nothing special. And then the next question is almost the same. Find the eigenvalues of the matrix and determine whether there is a sufficient number of to guarantee that the matrix is diagonalizable. Recall that the matrix may be diagonalizable even though it is not guaranteed to be diagonalizable by the theorem shown below. Let's say if an n by n matrix A has n distinct eigenvalues, then the corresponding eigenvectors are linearly independent. You see, if all eigenvalues are different, then corresponding eigenvectors are linearly independent, means they form a basis of the original space, and then the matrix A is diagonalizable. So here they give you matrix A 9 9 9 9. You check that easily. The next question, again, find basis B for the domain of T such that the matrix T relative to B is diagonal. Basically, we need to find eigenvalues, eigenvectors form, and then if all eigenvalues are different, then all eigenvectors are also different. So all basic eigenvectors, form a new basis where T is diagonal. I would like to show you the last question, that is 19, the question 19. Actually, the question 19 we already solved in the first test. So the problem 19 is some kind of application of diagonal matrices. So let's say if A is diagonal, is diagonalizable, and P is a matrix such that B is P to negative 1, A and P, right, is the diagonal form, means B is just diagonalized matrix A. Prove that AK equal to P, PK, P to negative 1. I mean, that's not a big deal. From this identity, if you multiply from the left of B by P and from the right of B by P to negative 1, so you will get the following one. P, B, P negative 1 equal to A. Right? Because each time when you have P with P negative 1, they will cancel out. And then from here, I have A equal to this. So what is AK? Let's say A squared, right? A squared is P, B, P negative 1, P, B, P to negative 1. I just multiply A twice. See, this is A, this is A. And inside, I have P to negative 1 and P. So that's why I have P, P. This guy is just identity. I don't write it. I have B, P to negative 1, which is P, P squared, P to negative 1. So similarly, when you have A3, A4, and so on, a K, you would get P, P to K, and then P to negative 1. This is what we need to prove. And then use the result above to find the power A to 5. Then we use this identity. Okay? Use this. They give us A equal to negative 11, and here's 18, 6, and 10, right? They ask us to find A to 5. So that means first we need to find this form. Or basically we need to find P, right? We need to find P. So we need to find eigenvalues, eigenvectors, and from that we find P. Then we plug P and P to negative 1 into this. In this case, B is the diagonal matrix where the main diagonal contains all eigenvalues of A. So basically, let's find eigenvalues, right? So I have negative 11 minus lambda, or maybe can we do something? Okay, let's do it. Negative 18 and then 6, 10 minus lambda. You take determinant, right? You set equal to 0. And then you have what? You have lambda minus 11 and then lambda minus 10 plus 6 times 18, 6. So I have A times 4, 100A, right? Equal to 100A. And that equal to 0. Let's say I have lambda in here minus 11 minus 2. I have minus 21 lambda. And here we have 110 plus with negative plus 2 1, 8 equal to 0. Oh my goodness. So you can use calculator or quadratic formulas to find solution of this, and then for each of them, suppose you have lambda 1 and lambda 2, you can find eigenvectors for lambda 1, you can find eigenvectors for lambda 2, and you set up P is the first column and the second column. And then what happened with P, right? So P in this case you would have so A K is equal to P diagonal in here, lambda 1, 0, 0, lambda 2, right? And P to negative 1. But if we have K here, so you just apply K to eigenvalues lambda 1 and lambda 2. And then you use hand calculator to multiply them back. So you get matrix AK. Make sense? Alright, so I think that is all for this practice exam. So together with video, so for practice test, I think you could solve most of problems in here. Watch them, prepare a little bit, and see you after the break. Have a nice day.